So in this video we're going to look at some examples of integration by parts. Let's begin with a pretty basic example. Suppose we're faced with integrating x times cosine of 5x dx. So the first order of business is understanding that this is an integration by parts problem. That's apparent to me because while I'd like to make a u equals 5x substitution, I can't quite do that because I've got this x out here, right? So I need something other than just plain u substitution to solve this. So integration by parts is a good choice. So what we're going to do is we're going to think of this x as being the u, and we're going to identify cosine 5x dx as being the dv. Then the integration by parts technique says that we can look at this instead of as the integral of u dv, but as the integral of, well, as uv minus the integral of v du. So what I like to do in these solutions is write off to the side a little thought bubble. All right, so we should try to do that. And I'll try to just uncover a little bit of this at a time so we can think through it. So then what I'm saying is that u equals to x, then if u is equal to x, well, du is equal to dx. If dv is cosine 5x, then if I integrate this, I get v is equal to, well, 1/5 sine of 5x, right? I'm making a little substitution there. That's why I've got a 1/5 when we integrate this, we get that. Now, if you're not sure about that, differentiate v. So dv dx would be equal to 1/5 times 5 cosine of 5x, right? Then multiply the dx to the other side, and we've got our dv is cosine 5x dx. All right. So when we're making an integration by parts, we have to do both identify a u and identify a dv. We have to make both at once. And then we go from there. Now, the integration by parts is only successful if, after using the integration by parts formula, we're left with an integral which is more manageable. Or at least it gets us closer to something. We'll see as we go on. So uv here is 1/5 x sine 5x, and then minus the integral of v du. Hey, well, that's not bad. Now I can integrate this using calculus 1 techniques. And so there you go. The answer is 1/5 x sine 5x plus 1/25 cosine 5x plus a constant. All right. So let's look at the next example. All right, just a comment here. To be successful with integration by parts, we need to select dv such that the integral of dv is actually a tenable calculation, right? If you can't integrate dv, then your choice of dv is not very good. So here's my next example. Integral of inverse sine of 3x dx. Generally speaking, when you're faced with the integral of an inverse function, integration by parts is often a good choice. And so we make u equal to the inverse sine of 3x. We make the dx equal to dv. Well, that's a good choice because certainly we can integrate dv. The integral of dx is just x, right? Now, if u is equal to inverse sine of 3x, remember that the derivative of inverse sine is 1 over the square root of the argument squared, and then the chain rule of 3x. 3x is the inside function. That's why I get this 3 from upstairs. So there's my du, 3x dx. 3 dx over the square root of 1 minus x squared. All right, great. So now I have my u, I've got my v, and I can put it down. There it is. So x inverse sine of 3x minus the integral of x times 3 dx over the square root of 1 minus 9x squared. Again, that's just the v du. All right, so this right here is something we can use a calculus 1 technique on. I'll make it w substitution since I've already used u and a v in a different sense. So if I let w equal to the thing inside the square root, then dw would be minus 18x dx. Differentiating that, I get a minus 18x, and then multiply the dx because we solved for the dw. And so that allows me to simplify that integral to simply minus dw over 6 over the square root of w. All right, then clean that up just a bit. So we really have 1/6 integral of dw over root w, which integrates to 1/3 the square root of w. All right. Now, if you don't believe me going from here to here, try differentiating this. When we differentiate that with respect to w, we get what? 1/3, 1 over 2 root w, but 1/3 times 1/2 is 1/6, gets us back to here. We can always differentiate the antiderivative to make sure we're in the right direction, right? Okay, going forward, of course, we don't leave our answer as w. We have to go back to the original x, undo the substitution, if you will. And so we're left with x inverse sine of 3x plus 1/3 square root of 1 minus 9x squared plus a constant. And there you have it. I think you start to hopefully appreciate the power of integration by parts. I don't think many of us could guess this formula as being an antiderivative of that, right? This technique has allowed us to find the function which, when differentiated, gets back to there, which is far from obvious. So this integration by parts technique is very powerful. All right, let's move on to example 3. So example, I've got too much stuff on my desk. Sorry guys, tell you what, I'll cover it up this way. There we go. So example 3, the integral of log x. Well, log is an inverse function. It's the inverse of the exponential, right? So integral of log x dx, we let u equal log, we let dv equals dx again. So dv equals dx integrates to v equals x. U equals log x differentiates to du is dx over x, because the derivative of log x is 1 over x. We use integration by parts. So I write the formula down again just to make sure I do my steps right. And I've got x log x, right? That's the v. I put the v first and the u second just because I like to write x log x, just a question of style. And then here the x's cancel, right? And we're just left with the integral of dx, which is x again, but there's a minus. And so there you have it. X log x minus x is the integral of natural log of x. And by the way, I'm assuming that x is greater than 0 throughout example 3. All right, so these 3 examples I've showed you so far are pretty standard. Let us go on to another standard example, which has a rather different flavor to it. Here we face the integral of e to the minus x times cosine of 3x of dx. So we're going to let u1 equal e to the minus x. We're going to let dv1 equal the cosine 3x dx. And the reason for putting a 1 here will become soon apparent. So great. u1 v1 is this. And now I can't well, let's see here. I can integrate cosine 3x. That gives me a minus, let's see here. It gives me, 1/3 sine 3x is my v1. Now u is e to the minus x, which makes du minus e to the minus x dx. There's my du1. And then I take the minus from the integration by parts formula and the minus from the differentiation of u1 rather, and that gives me a plus. And oh no, now I've come to something which is almost looking as bad as that, right? But the neat thing about this problem is if you do integration by parts again, if you let u2 be that and you let dv2 be that, then, and by the way, parentheses are your friends, so I put these parentheses here like that, all right? We get 1/3 e to the minus x sine 3x. And then, again, the integration by parts formula gives me this in here. But look at that. That's cosine 3x e to the minus x dx again, which is what we started with. So we've begun with this, which I'm calling I, and we ended with this again here, which is I, but it's not just I, right? There's a minus, there's a 1/3, there's a 1/3. So this is actually minus 1/9 I, if we clean things up, all right? So in summary, we found the following formula. We found that I is equal to 1/3 e to the minus x sine 3x minus 1/9 e to the minus 3x cosine 3x minus 1/9 I. So then I do algebra, right? And I add 1/9 I to both sides. 9/9 plus 1/9 is 10/9, so I get 10/9 I is equal to that, and voila, I have solved the problem. We find that the integral of e to the minus x cosine 3x is 3/10 sine 3x minus 1/10 cosine 3x times e to the minus x, and I have to add a constant, right, because we're looking for the antiderivative. Well, we're not looking just for an antiderivative, we're looking for the most general antiderivative when we do an indefinite integral, right? So we add a constant to reflect the fact that we're not just thinking of one antiderivative, but the whole family of them, any of which differentiated gives me back this integrand. So when I see something that works out like this, I say that the integration by parts loops. There are other problems where you have to go 3 steps before it loops back. I don't know if I have one of those in your set of examples, but it's possible. Move stuff off my desk so I can... All right, here's another one. Come on. All right. So integral of x squared sine x dx. This also requires 2 integration by parts, but this one doesn't loop. It just gets nicer. So x squared sine x dx, I do my first integration by parts. I let u1 equal x squared, which gives me du1 is 2x dx. I let my dv1 be sine x dx, which integrates to minus cosine x. All right. So I've got my uv minus the integral of v du, but there's a minus in the du, which I canceled with the minus in the integration formula. So I just took the training wheels off, guys, right? I stopped writing uv plus v du. And you can do the same once you understand. You do need to write work down, of course, but, you know, well, anyway. So here, that's getting better, right? We've gone from x squared to 2x. And then we do, I clean it up a little bit, right? And then I go, oh, wait a minute. I can do integration by parts again. I can let u2 equal x, and I can let dv2 be cosine x dx, right? And if I do that, then u2 v2 is x sine x minus the integral of v2 du2 is just, well, v2 integrates to sine, rather dv2 integrates to sine, and du2 is dx. So we get that. And then be careful with the parentheses. The parentheses are so important. If you don't use parentheses here and be careful to pay attention to them, you won't know that you should distribute that too to this part as well, right? So this sine integrates to minus cosine, but that minus gives me a plus, and that 2 multiplies both of these. And there you have it. So this also required 2 integration by parts, but we didn't have to, it didn't loop. We didn't have to do algebra at the end. It just works out nice and pretty like that. Pretty standard example right here. All right, moving along here. So I would encourage you, you know, it would be a good idea at the start of any of these examples to just stop and try to work it out for yourself and then see what I do, right? Probably you need to pause after I first put up the problem. And it might even be better to not even look at this part. All right, anyway. Integral from 0 to 2 of y sinh. Now, the sinh, or the hyperbolic sign, all right, of y dy, this may be a function you haven't seen before. We'll talk more about that as we go on. So what we're going to do here is u is equal to y, dv is sinh y dy. Turns out the integral of hyperbolic sine is hyperbolic cosine. And so this is integration by parts formula again. So we get uv, which in this case is y cosh y, evaluated from 0 to 2, minus the integral of v du, which in this case is cosh y dy, integrated from 0 to 2. Now the integral of cosh is sinh, and so we get cosh of, so this we get cosh of 2. Oh no, what has happened here? Oh no. Oh, wait a minute. I was worried. I thought I had missed the 0. But the reason that 0 doesn't contribute is I've got that 0 there. So I get 0 cosh 0. Now cosh of 0, or hyperbolic cosine of 0, is 1. So just in case you didn't know, let me just pause here for just a second to mention a fact for you in case you didn't know. And that is that. Sorry to break the flow of this one, but it occurs to me I should probably save this here. Sinh of y is 1/2 e to the y minus e to the minus y. Cosh of y is 1/2 e to the y plus e to the minus y. So this is an odd function. This is an even function. They're respectively the odd and even parts of the exponential, we have that e to the y is equal to cosh y plus sinh y, in fact. And, well, we could say more about it, but for now I'll just tell you the main thing is that the derivative with respect to y of cosh y is equal to sinh y, and vice versa. I can't decide whether or not I need parentheses. I mean, it's debatable whether or not you need parentheses in this situation. Should be clear enough. So anyway, that's the calculus of hyperbolic sine and cosine in a nutshell. You can derive these from the definition. It's not a big deal. All right, moving on. Oop. Oh no, I need my cover sheet. All right, so with that in mind, it's simple to see that cosh of 0 is 1, and that sinh of 0 is 0. So this leaves us with 2 cosh 2 minus sinh 2 is the answer. Move on to example 7. Example 7 is a little bit more adventurous. Here we're asked to derive that the integral of the nth power of cosine is 1 over n cosine to the n minus 1 power of x sine of x plus n minus 1 over n integral of cosine to the n minus 2 power of x dx. All right. So this is allegedly true for n, I suppose, greater than or equal to 2. And here's how it goes. So I initially tried this, and you know what? It didn't work out. And that's an important thing we don't show you too often in videos, is that a lot of the process that you need to make is to trial and error. You got to try things, and sometimes they work and sometimes they don't. All right, just because everything I do tends to work, it's just because, well, you know what? I've done pretty much nothing but math my entire adult life, so, you know, I tend to know what I'm doing. You're learning, so you make mistakes, and that's okay. You just have to keep trying. All right, so here's how we should try this. So cosine of n of x dx, we can rewrite that as cosine to the n minus 1 times cosine of x dx. I'll think of this as being my du. I'll think of that as being my dv. Now that's hopeful because I can actually integrate this, right? Again, whatever we choose for dv, it's got to be something we can integrate. If we can't integrate the dv, then there's hardly a next step, you know? So then this is uv minus the integral of v du, all right? And that simplifies a little bit because we get sine times sine, which gives me sine squared, and I pull out an n minus 1, this minus and that minus cancel to give me plus. Now this sine squared I can convert to 1 minus cosine squared by the Pythagorean identity. And then, what do I have? Well, I have the integral of cosine to the n minus 2 times n minus 1, right? Minus this n minus 1 plus the integral of, well, again, this times that gives me cosine to the n again. Oh, look at that. This looped. This and that are the same, right? Except that there's a difference because this one has the minus 1, minus n minus 1 coefficient, whereas that just has a coefficient of 1, right? So if we solve this for I, so I've got I equals this minus n minus 1 times I. So if I solve for I, which would amount to adding n minus 1 copies of I to both sides, that would give me ni on the other side if I add it to both sides. And then I divide by n. So integral of cosine to the n, 1 over n, sine of x, cosine n minus 1 of x, plus n minus 1 over n, that, which is what we claimed. Again, this last step is just algebra. Make sure you understand it. Let's see here. So there are similar recursive formulas for sine, tangent, and other functions. And I tend to recommend using a more direct approach for like integral of sine squared or sine cubed. We'll see that in one of our upcoming videos on integrals of trig functions. All right, moving on. Example 8. Excuse me. So in example 8 here, we face the integral of t cosecant squared t dt. So we're going to let u equals to t, we're going to let dv equals to cosecant squared t dt. Now this is a good choice because we remember that the integral of cosecant squared is minus cotangent. All right, now that minus has gotten balanced out by the minus in the integration by parts formula to give me a plus. du is dt. So here's the thought bubble on the side there. So then this gives us minus t cotangent t plus the integral of cosine t dt. Now this is just what cotangent is. It's cosine over sine, right? And with that made explicit, it's clear how to integrate. We just let w equal sine t, then dw is cosine t dt, which gives us dw over w, which integrates to the log of the absolute value of w. Those absolute values are important. Leaving them off will get you into trouble. And so we get minus t cotangent t, put back in w is sine t, natural log of the absolute value of sine t plus a constant. And there you go. All right. Let's see, I have yet another example. So this one concerns cylindrical shells, which is something that you may or may not have seen in Calculus 1, so it's good for us to stop here and look at this one. We're supposed to use the method of cylindrical shells to find the volume bounded by rotating the bounded area, or maybe I should say area bounded, by y equals cosine pi x over 2, y equals to 0, for 0 less than x less than 1 about the y-axis. So whenever I'm faced with a question like this, the first thing I do is I try to draw a picture to illustrate what I'm doing. So here's a picture. This is the area. This is cosine of pi x over 2. When you plug in 1, you get cosine pi over 2, which is 0. When you plug in 0, you get 1. So this is actually this part of it. This is that graph of cosine, all right? So we're taking this quarter of the circle, if you will, quarter of the disk, and we're rotating that around the y-axis, all right? That's what this little circle means. And so what you have to imagine is if you took this kind of, and it would make a hemisphere, right, a half of a sphere, and you could chop it, if you think about it, you could chop it up into these little cylindrical shells, and if you were to add the volume of each one of these little shells up in total, you get the volume of the entire hemisphere. So that's what this picture is. I am envisioning the cylindrical shell. It's going to have a height of cosine pi x over 2. Oh, did I say this is a sphere? That's not quite honest, because this is the graph of cosine. It just, my picture kind of looks like it would be a sphere. It's not quite that. It's something else. But anyway, it's kind of like a sphere. Maybe a squished sphere. Don't be distracted by my technical nonsense. All right, so cosine pi x over 2 is its height. Its thickness would be dx, right? And if we were to lay that shell out flat, the dv it would have would be the length of it, which would be the circumference, which would be 2 pi x, right? And the height would be y, which is cosine pi x over 2. The thickness would be dx. So to get the volume of a cubicle, well, a slab like this, we do the area times the thickness, right? Which would be 2 pi xy dx. And that's why I say dv, the infinitesimal volume of the cylindrical shell, would just be 2 pi x cosine of pi x over 2 dx. So we just need to integrate that, right? Which is the way we take a continuous sum from 0 to 1. And that should give me the volume of this solid of rotation. Again, add up all the little dv's by integrating. And so here it is. But the interesting thing, of course, about this integration is it is an integration by parts. So we have, this is much like the first example, right? It's an x times a cosine. Now we've got some extra pi's and stuff floating around, but it's basically the same example. I let u equals this, I let dv equals that. My bounds are 0 to 1. So this is u, that's v, integrating cosine. Pi x over 2 makes it 2 over pi times the sine of pi x over 2. You can try it. Differentiate that. You'll get back the dv like you should. And then we're supposed to evaluate from 0 to 1, and then we get minus the integral of, v du. And so when I plug in 0, I get 0. When I plug in 1, I get 2 pi times 2 over pi times the sine of pi over 2. Well, sine of pi over 2 is 1, right? And so we get 4. Actually, so this works out to 4. And then that, I have to integrate that, right? And so this gives me minus 2 over pi cosine pi x over 2. I have to evaluate that from 0 to 1. Again, the first term gives me a 4. And the second term gives me, 2 times 4 is 8. And I got a pi. And then I've got a cosine pi over 2, which is 0, by the way, and the cosine of 0, which is 1. So I get a subtraction from the fundamental theorem of calculus, part 2 there. And that leaves me with 4 minus 8 over pi. 4 minus 8 over pi is the volume of this curve revolved around the y-axis. So this is the method of shells. If you haven't seen it before, it would be a good idea to go find the section in your textbook on this and read about it. Let's go on to example 10. So I don't always have this many examples, but integration by parts is a pretty important technique, so I thought it would be good to give us a lot of examples to get started here. Calculate the average of the function x secant squared x on the interval 0 to pi over 4. So how do we calculate the average of a function? I'll remind you, what we do is we integrate the function over the interval and we divide by the length of the interval. That's the average of a function. So here it is. F average is 1 over the length of the interval, which is pi over 4 minus 0. And then we have to integrate. All right, that's just the definition of the average of a function. All right, I'm going to calculate this integral to start with, then I'll return to star. So here you go. Integral of x secant squared x, so I make my secant squared x dx my dv, because I know the integral of secant squared is tangent. That's a basic integral from Calculus 1, we all know that. So I've got uv, which is x tangent x, minus integral of v du. V again is tangent, du is dx. And then we got integral of tangent. Well, that is a pretty well-known integral from Calculus 1 as well. That's solvable by a u substitution, but I use a w here because, well, we already used u for something else. And so if we let w equal cosine x, dw is minus sine x dx. But you know what? I've already got a minus there, so I can use that minus to get my dw. So I got plus dw over w, which integrates to log of the absolute value of w. But of course w is cosine x, so there you go. X tangent x plus the log of the absolute value of cosine x plus a constant. Now, that's just the antiderivative, or the indefinite integral, if you like, of the function. Now I need to actually calculate it as a definite integral. I have to take care of the bounds. So here it is, and it's gonna not quite fit on my sheet unless I shift it up a bit here. So 4 over pi, because by the way, 1 over pi over 4 is 4 over pi, right? And so then I just take that antiderivative I just worked out, put it down here. I have to evaluate from 0 to pi over 4. So that gives me, at the upper bound, pi over 4 times the tangent of pi over 4. Of course, the tangent of pi over 4 is 1. And then we have the natural log of the cosine of pi over 4. Well, the cosine of pi over 4 is root 2 over 2, right? And let's see here, when we plug in 0, we get 0 from this. Cosine of 0 is 1, so the natural log of 1 is 0. Evaluating at the lower bound gives me 0. So the only upper bound is the only thing that matters. And there you go. So we get 1 plus 4 over pi times the natural log of 1 over root 2. Cosine of pi over 4 is 1 over root 2. And you notice that this and that cancel to give me 1. But on the other hand, it also distributes over to this term to give me 4 over pi times that log. So there you have it. The average of x secant squared x on 0 to pi over 4 is in fact this. Now, I'd like to point out something. You might think that I didn't need to pick up a calculator just because I wrote this before I had this video. That's not the case. I didn't need to pick up a calculator because these are known values of tangent and cosine. So knowing those is helpful to you. If you have to pick up a calculator to do everything I just did, it slows you way, way down. So there's certain, standard values of sine and cosine that you should be familiar with. Things like tangent of 0 being 0, cosine of 0 being 1, the natural log of 1 being 0. These are common knowledge at this point in your mathematical experience. Now, they may not be common to you yet, but I hope they become more known to you as we go on. All right. I mean, you do have a calculator on the test, so you can do it, but it takes you time, right? And it's valuable time. You could be thinking about calculus rather than looking up a easily known value to a function. And example 11. This one's a little bit more theoretical. But that's part of the reason you're taking calculus, is so that you can understand theoretical calculations and whatever your major is. Calculus is the language of science, and understanding theoretical calculations in calculus is as or more important than the kind of examples we were just going over. Even if I don't test on it as much, it doesn't make it any less important. Anyway, so suppose we have f of 0 and g of 0 is 0. And suppose that the second derivatives of g, f prime prime and g prime prime, are continuous. We're asked here to show that the integral of f times g prime prime from 0 to a is f of a g prime of a minus f prime of a g of a plus the integral from 0 to a of f prime prime of x g of x dx. So when you first look at this, it may be kind of like, ugh, but it's actually not bad. Let's see how. So what you got to do is just start picking at it. And what I do with a problem like this is I just say, okay, I'm gonna focus on that, see what I can say about it. So I'm going to think of g prime prime of x dx as my dv. That's good, because we know we can integrate the second derivative to get the first derivative, right? And then we can differentiate u to get f prime. So this is v du, and there's my u and my v. All right, I'm going to call that star. Let's see here. Then, continuing, so that's just, what's here is just what I just talked through. Then the integral of, so then what I'm doing, just to recap here, so I picked it at this part, now I'm picking at that part, all right? So the integral of f of x, f of x g prime prime of x dx is, so this is by, oh, I'm sorry, I'm being an idiot. Let me just, nothing, all I'm doing is continuing from star. So evaluate from 0 to a, f of a g prime of a minus f of 0 g prime of 0, but we're given f of 0 is 0. So this just simplifies to f of a g prime of a, and then minus the integral from 0 to a of f prime of x g prime of x dx. Now, next I'm going to do integration by parts again, letting that be u2, let that be dv2. And when I do that, so this just comes down to there, and integration by parts on this goes f prime of x g of x. All right, so that's my u2 v2 minus the integral of v2 du2. And these parentheses keep us in order. They make sure we distribute that minus to both of these terms. All right. And so there we go. Then evaluate from 0 to a, or from a to 0, depending on how you read it. We have f prime of a g of a minus f prime of 0 g of 0. Now that's given to us to be 0, so that just leaves us with this minus that, and then minus gives me plus. And that is what we're asked to prove. We're asked to prove that this is equal to that. And you see we can show that by just applying integrate by parts carefully 2 times, and the identity pops out. So finally, I think I have one more example for us, and then we'll be done. Example 12. So here I'm confessing that you're supposed to know cosh and sinh. These we do expect you know. I will test on them. So cosh squared minus sinh squared is equal to 1. That's the sort of analog of cosine squared plus sine squared for the hyperbolic sine and cosine. And here's a problem. So I'm asked to integrate the inverse hyperbolic cosine of x dx. So this is an inverse function. Integration by parts is a good go-to. So we do u equals inverse hyperbolic cosine, dv is equal to dx, and this is uv minus the integral of v du. Now du here, I realize you might not be familiar with yet. Here's the derivation. If you didn't know how to differentiate inverse hyperbolic cosine, here's how. We set y equals to inverse cosh. We take the cosh of both sides. We differentiate implicitly. That gives us sinh y dy dx equal to 1. We solve for dy dx, 1 over sinh y, and then we can, well, y is inverse hyperbolic cosine, so we have d dx of inverse hyperbolic cosine, and the sinh y we can solve for if we put a y up in here. That gives us that cosh squared, well, it gives us that, put it on the other side, sinh squared y is equal to cosh squared y minus 1. So square root gives us that. And so there's the derivative of inverse hyperbolic cosine is 1 over the square root of x squared minus 1. In contrast, inverse cosine is 1 over the square root of 1 minus x squared. And I think there's a minus. Yeah, there's a minus on the inverse cosine. Anyway, so there's your du, and there's your uv. And again, this is a w equals x squared minus 1 substitution, which gives us dw over the square root of w minus 1/2, like so. And integrate, and then plug back in the w. And there you have it. The integral of inverse hyperbolic cosine of x dx is given by this formula right here. So again, just to recap, integration by parts is a useful technique. And the one thing you should be thinking about as we're going through all these different examples is how on earth did I choose the u and the v, right? What's the strategy for choosing u and v? So I'll tell you this as we go. A lot of people find that, and it's just kind of silly, but it's sometimes helpful, that this is a strategy. So this stands for log, inverse function, algebraic, trigonometric, and exponential. This is the sort of your choice of u. So if we choose u according to this rule of thumb, it's often helpful. If we go back and review the examples, let's see if we can see that pattern. All right, let's go back to example 1. Here we go. Tour down memory lane. Example 1. What did I choose? U equals x. Was there a log? Nope. Was there an inverse? Nope. I have a hard time looking at this liate, as it's sometimes called, because to me, anyway, fine. I see inverse functions here, but it's because of my mathematical nature. You don't see inverses there, so great. Is there an algebraic function there? Yes, it's x. That's why I chose x equal to u. All right. Let's see here, next example, inverse sine. Is there a log? Nope. Is there an inverse function? Bing, 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 bing. So we chose inverse function was the u. All right, great. Example 3. Let's see here. What do we got? Log. Oh, log. So we make u equal to log. Yep. What do you know? All right. This one's a little bit of an outlier. Let's see here. Is there a log? Is there an inverse function? Is there an algebraic? Well, there's a trig. I could have made u1 equal to the cosine 3x. This one actually, there's a couple different ways you could do this example. So, oh well, I guess the liate has let us down here. This is just a rule. This is not a law of mathematics. It's just a general guide. It's often helpful. Let's see if it worked for the next one. This one. Let's see here. Log, no log, inverse, not really. Algebraic, oh, algebraic, yep. X squared was my choice for u1. What do you know? It worked again. How about this one? Sinh y dy. Y is an algebraic function. We chose y, u equal to y. What do you know? Worked again. Let's see here, 7. And this one is not quite the kind of thing that liate works for. So I'm just going to go on. Let's see here. You got your t, you got your cosecant squared. Algebraic comes before trigonometric, which is u equal to t. What do you know? Again, this is just a rule of thumb. This one, after we got through the setup, we've got x times cosine, and we made the 2 pi x our algebraic function. Yep. Let's see here. This one was x secant squared x. Again, we had an x times something we know how to integrate, so we made u equal to x. All right. Finally, this one doesn't really apply because this is a theoretical problem. And then finally, the last one, cosh inverse, log, nope, inverse function, bing, 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 so we made u equal to cosh inverse. So this was pointed out to me by students about, I don't know, 15 years ago. And it's often successful, but I would encourage you, instead of relying on some silly partially defined mnemonic, to instead, do homework until you're comfortable with the method. So anyway, with that, I will stop. Thanks, guys.